Hello, it's Keith here, and this is lesson 1 of what I'm referring to as the MinTile series of my 68000 assembly programming tutorials. What's MinTile? Well, MinTile is designed as a minimal tilemap routine. What this is a tilemap drawing routine, and also it simulates sprites using that same tilemap code. And it's been written on all of the systems in my Z80, 6502 and 68000 tutorials, and it's the same port of the code that works in the same way. And the idea is that firstly, this could give you an example of how to do tilemaps on systems that don't have tilemaps, like the Atari ST or the BBC for the 6502 and things. You know, these don't have tilemaps, but maybe we want to do one. How can we do it? Well, this is an example, and also just an example of how to do things in a common way of multiple systems. For example, you can see on the screen here we've got the NeoGeo version that is using the fix layer, which is actually a tilemap. So that is doing this example here, it's running the code. But then if I switch to another example, well, I've got an example here, which is another NeoG example. And this is the almost exact same code running, but this time we're going to use the hardware sprites. So the NeoGeo doesn't have a genuine tile map. It has the fix layer, which is very much like a tile map, but it doesn't have a tile map for the in-game graphics as such. Fix layer is really designed for fonts. And so what we have to do is we have to align lots of hardware sprites into a tile map. And you can see one here. And this is basically the same code. We've got our characters, which are hardware sprites moving around. And then if I press the first fire button, we can scroll the screen. Now, you'll notice the background tiles look different there. The reason for that is I didn't redefine the sprites. They're the wrong size. They need to be double sized. For this example, it didn't seem worth it. But the code is basically the exact same code because it's the hardware abstraction layer, the platform-specific tile drawing routine that's changed. Everything else is exactly the same. And we're going to see part of that multi-platform code today. So let's take a look. What we're going to look at today is the very basic bits. There's the CLS routine, which is basically the ClearScreen routine that redraws the entire tilemap in one go. And we're also then going to look at the draw tilemap routine, which is part of the code that handles the simulated sprites. I'm referring to them as sprites, but they're actually a miniature tilemap object. Basically, if we have a look at one of these examples here, the Chibico mascot that you saw moving around the screen is actually a small tilemap. That's the Chibico mascot tilemap. This is the background tilemap, and so it's just a slightly tweaked version of the code that is drawing that to the screen with the same platform-specific tile drawing routines, and that is to reduce the amount of platform-specific code and make it easier to port this to so many systems. So say MinTile is a minimal tilemap, very crude, lots of limitations, but viable and quick to port to new systems. So that was the benefit of it. Anyway, let's take a look at the ClearScreen routine. Now, the first thing we're going to do is we're going to load the A6 register with the base memory address of our screen. Now, this is different on every system. For example, if you look at the Sinclair QL, here is the screen base for that system. NeoGeo is a bit of a quirky one, though. It kind of works differently. So the NeoGeo, we're actually defining an X and a Y position here for the grid of sprites that the NeoGeo will use. What we're then doing is we are loading the draw height into D7. Now that is 1/8 in hexadecimal, that's 24 tiles, that's the height of the screen. We're loading the draw width here, that's 32 tiles, that's the width of the screen. And we've got this routine called DoStrip. Now this is a platform specific routine. So what this does is it will draw an entire horizontal strip of tiles in whatever way is appropriate for that system. So on a bitmap system, it's going to transfer bitmap data. On a hardware tilemap like the NeoGeo, it's going to address that tilemap memory or address that predefined sprite, and it's going to set the tiles accordingly. So let's just very quickly take a look at the Sinclair QL1. The Sinclair QL1's a nice bitmap screen, a nice crude bitmap screen, so it gives a very maximal example of the kind of work we might have to do. The bitmap ones are much quicker. So here is the DoStrip routine, and so what we're going to do basically is we are going to load a tile in from the memory address A2. A2 is pointing to the source tilemap data, so that is our Chibico tilemap maybe, or our background tilemap, and we're going to check, and if that's a 0 tile, then there's nothing to do. 0 is defined as idle. Basically, we're just skipping over this tile. Otherwise, we're going to want to update the visible tile though. Now, the system uses what's known as a tile cache. This is a change sequence. Basically, the tile cache is the updates that need to be made to the visible screen. MinTile, because it's designed to work on 8-bit systems with limited memory, doesn't use a double buffer. So it works with a single buffer, and the cache is just the updates that need to be drawn to that visible screen. So if a tile is being drawn and we are clearing the screen after, which is marked by the tile clear variable, we're going to write a 0 to that entry, clearing that entry of the tilemap so it's not updated again. What we're then going to do is we're going to load A3 with the address of the tile source data. What we need to do is we need to calculate the offset for the pattern that we want to show to the screen based on the number of bytes per pattern. So we're multiplying that up here and we're adding it to the source data. Now the source pattern data is in A5 here, so that's our source patterns. We're adding that, we're adding the offset here, and so A3 is now the source bitmap data. We're then moving A2 to point to the next tile, and what we're going to do is we're going to transfer all of the source bitmap data from A3 to the screen A6. We're just going to do that in whatever way this system requires. Now, in this case, moving one 32-bit value is enough to draw one full tile on the SyncQL, but on other systems it won't be. And then to move down one line of the screen, we're just adding 128 and we're repeating. So that's what we're doing on this system. But this routine here, this DoStrip, will draw an entire single strip to the screen and then it will return. And it does some correction of the A6, the VRAM destination, but it doesn't necessarily update it to point to the next line, because what it will need to do will depend on what kind of line it's drawing, so it doesn't try to. This isn't so important on the 68000 systems, but on the Z80 systems and 6502, performance was extremely limited, so doing calculations that might not be appropriate was a waste of resources, so I didn't do them. So we're doing our DoStrip here. We're drawing 32 tiles, one full visible line of the screen on most systems, maybe some are 320 pixels wide. We always work at 256 though. Now after that line, we then need to make some corrections to our A6 variable, because as I say, that's the VRAM destination. It's probably pointing to the end of the line and we want to point it to the start of the next strip. So we've got various calculations here that we're doing here to correct and point A6 to the correct position for the start of the next strip. We then simply repeat for the next line of the screen. We do the remaining 24 lines, drawing the entire screen to the screen. As I say, no second buffer. Now, of course, these 68000 systems, the vast majority of them are going to be capable of some kind of double buffering. So worrying about working within a single buffer is possibly unnecessary. However, as I said before, by working with the minimal amount of resources possibly available, just a single buffer, we allow the code to be as portable as possible. And by working in the same way on every system, we aren't giving ourselves excessive resources on the systems that have them, so that we are forced to work within that minimal capable specification, and that makes it easier to port again to more systems. So that's why I'm doing that. So that's the CLS version that draws always the full width and the full height of the screen. Now the alternative version is the ToDo Tilemap version, which we're going to look at right now. So this is pretty similar, but basically all it's going to do is it's going to draw a smaller tilemap to a central part of the screen. So what we're going to do first here is we're going to check the strip routine. Now the strip routine will be 1 if we need to reverse the sprite, so we can X-flip the sprite. MinTile can't do Y-flip. I'm working on a later version called MaxTile which will do that, but this version can only do X-flip. So what we're going to do here is we're checking if we're doing the reverse version here, and if we are, we're going to jump down to here. What we're then going to do is we're either going to run DoStrip, or on a very limited number of systems, i.e. only the NeoGeo, we're going to run DoStrip Sprite, and that's because of the hardware sprite capabilities of the NeoGeo. So we've got a special version for that system, but generally speaking, we're just going to run DoStrip on everything except the NeoGeo. Basically, that's a sort of tweak for the NeoGeo's weird hardware sprites. So that's going to draw an entire line. DoStrip Sprite Reverse, or DoStrip Reverse, will basically X-flip the data. This is done in real time. The bitmap data is flipped, or the hardware sprites will be set to flip. So that's what's happening there. So this time what we're doing here though is we're actually backing up A6, which is our VRAM destination here. So although we're moving across the screen, because we don't know how much we're going to move across depending on that sprite, we're just backing up and restoring A6. And so when we get back here, we're restoring it, and then we're going to start from the next line. We're also backing up A2 as well, and again that's because we don't actually know how much of A2 we have actually done. You know, maybe the sprite is cropped, but we need to move down one full line before we start drawing the next line. So when we get here, we're basically going to update A6 accordingly, effectively moving down one full line on the NeoGeo. That's adding one. That's actually for the fixed layer. The fixed layer is rotated 90 degrees because everything on the NeoGeo seems to be weird. But on the other systems, these are the calculations to move us down one full strip of 8 pixel tall tiles. We're then adding D7 to A2. A2 is our source tilemap, and D7 is the width of that tile map. As I say, it could be cropped, which is why we're doing that. If it wasn't cropped, we wouldn't need to, because by the time we'd drawn one full line, we could just carry on from the next part. But as I say, if we're only drawing half a line, it's cropped, so we need to correct width for that. And then do tilemap reverse. This is the version that does the flipped version. Basically, all we're doing here is we are doing a correction of the tilemap position. When we're drawing our reversed sprite, basically we draw from left to right still, but we process the tilemap data from right to left. So what we're doing here is we're moving from the first tile to basically the last one of that line. If you look at the tilemap data, for example, this Chibico sprite here, we would normally start from that tile there, but if we're reversing it, we want to start from this tile here and move backwards. So that's what we're doing here. So we're just calculating to move to the far end of the current line here, and then we're setting the strip routine to version 1 here, the reversed one, drawing the tilemap, and then setting it back to 0 for the normal one. And there we go. So that's all we're going to cover today. We're going to go into more details next time. There's lots more of it. As I say, you're welcome to on my website, download the source code and the build scripts, have a go with it. And if you can use parts of it, do so. And if you somehow manage to use it commercially, please do so. Don't need to give me credit. And as I say, in a lot of ways, the 68000 version of this isn't really that necessary. The 68000 versions don't really need much coaxing to do hardware tile maps. A lot of the systems can do it anyway. But again, this is more about writing code that works in the same way across a large number of systems and CPUs. So if you want to see this on a more tricky system, try the Amstrad CPC with its massive 12K screen and its tiny Z80 processor. That's a bit more of a challenge. Anyway, hope you enjoyed what you've seen today. Thanks for watching, and goodbye.